We want to define cup product in torus. So this is how the torus looks like. You identify these two sides, say A, and then you identify these two sides, say B. So the homology groups and cohomology groups of torus coincide. So this is the 0th homology and cohomology group, just integers. The first homology and cohomology group, which is integer direct sum with integers. Second cohomology group is just integers. So we know in the cup product these are just identity elements. So these are just ID. So if you take cup product with this, nothing is going to happen. On the other hand, consider elements here in H2. So you cup elements in H2 with elements in H2. So if you take element in H2 and cup it with H2, you land up in H4. But this will only lead to 0 because higher cohomology groups are all 0. Similarly, if you take an element in H2 and cup up with element in H1, so H2 and H1, this will lead you to H3, 2 plus 1, 3. And H3 is again 0. So higher elements are 0. So only thing we need to focus on is this, the first homology or cohomology group. So we focus on this. Okay. Now, if you consider homology here, you know that this is generated by edges. So the edges are A and B. So say this is coming from edge A, this is coming from edge B. Now corresponding to these edges, you also have cohomology groups. Cohomology groups corresponding to A, it is alpha. Say corresponding to B, it is beta. So how do these cohomology groups act? So what we want to find is that alpha coupled with alpha, this will land in H2. How does it look like? And alpha coupled with beta lands in H2. How does it look like? Beta coupled with beta, how does it look like? Now, if you want to do this alpha coupled with beta, you can't apply it on all vertices. So let me number the vertices. There's actually one vertex here, but we will number it as 0, 1, 2, 3. So once you make the torus, all these four identity get identified to one point. So if you take like this is a problem, right? Because alpha will act on 0, 1 and then beta will act on 1, 2. So this 3 is hanging out, and anyway this is, if you write it like this shows this is in C3, but what we want is C2 because alpha is in C1, beta is in C1. You cup them, you should land in C2, but you can't have 0, 1, 2, 3. So we need to rectify this, and that is very simple. We just draw an edge from here to here. Say we draw it like this, and now you can do it, you know. So now you can you have two triangles, and you need to take in mind the orientation. So the orientation here is like this. So the first triangle will be 0, 1, 2. So from 0 you go to 1 to 2. You're just following the arrows. And the second triangle is, again, you need to keep orientation in mind. This is going like this, and that is 0, 3, 2. 0, 3, 2. So these are the two triangles on which we will work. So on these two triangles we want to find alpha cup alpha, alpha cup beta, and beta cup beta, and all three will land in H2. Yeah, because alpha is coming from H1, this is from H1. So alpha is from H1 and beta is also from H1. So this is what we want to compute. So alpha cup alpha on 0, 1, 2. So this is what we have to compute. But what is this alpha on the edge? So even if I write it like this, what is this alpha on the edge? So basically we say that, you know, this alpha is nothing but a map. Alpha is nothing but a map which is acting on the edge. So that is a definition of cohomology. You know, alpha is a map which acts on this edge. And where does it take this edge to? It takes this edge to integers. Now we are working in integers. Our ring is integers. So you have this edge here. say edge is 0 1, right, this edge right here. So alpha acts on it. What will it do? It will take it to, it cannot take it to all the integers. It can take you to one of the integers, and we just take that integer as 1 because 1 is a generator. You could also say 2, you could also say 3, or so on. So you could have all the generators here. So this 0 1 takes to 1. Yeah, so this is what alpha is going to do. It will take this edge to 1. So let us draw this alpha so that we understand. Yeah, so alpha acts on is acting on this edge A. So say it joins these two edges or acts on these two edges. But if it acts on these two edges which are identified with each other, it also acts on this edge 0 2 which I have drawn. So alpha is taking value 1 on 0 1, 1 on 0 2, and 1 on 3 2. Similarly, you can talk about beta. So this is beta. It joins B. It's corresponding to B. You see here, B is here, beta is here. So it is beta is 1 on 0 3, beta is 1 on this 2 0, and then beta is 1 on this 1 2. So again, you have to keep in mind the orientations. The arrows are very important here. So let us focus on this triangle first, 0 1 2. So alpha cup alpha 0 1 2. So alpha of 0 1. So alpha acting on 0 1. This is just 1. Alpha acting on 1 2. Now alpha does not act on 1 2. See, alpha is this rust line. It is not touching 1 2. So when alpha is not touching 1 2, it is just 0 here. So if the edge is not there, so alpha is not even crossing that edge, so it is 0 here. So 1 times 0 is 0. Now alpha cup alpha on 0 3 2, alpha cup alpha on this 0 3 2. So you have taken this triangle according to the orientation 0 to 3 to 2. So alpha acting on 0 3, there is no alpha here, rust color line is not even touching here, so this is 0. But alpha on 3 2 is 1, but 0 times 1 will give you 0. Now beta cup beta on 0 1 2. So beta on 0 1, so 0 1 is here, and beta is this purple line, doesn't touch it, so this is 0. And beta on 1 2 is 1, but 0 times 1 will give you 0. Now beta cup beta on 0 3 2, 0 3 2. So on 0 3 beta is 1, it's touching right here. On 3 2, this magenta line doesn't touch 3 2 at all, so it is 0 here. 0 here, but 1 here. 1 times 0 will give you 0. Now alpha cup beta on 0 1 2, 0 1 and 2. On 0 1 alpha touches here, you get value 1. On 1 2 beta touches here, so you get value 1 here. So you have 1 times 1 which will give you 1. And on 0 3 2 alpha acting on 0 3. So alpha acting on 0 3, there is no alpha here, so you get 0 here. Beta acting on 3 2, so beta on 3 2 is again 0, it is 0 here, so you get 0 here. So this is the generator. So the generator is in this triangle 0 1 2. So the generator is right here in this triangle. So this is our generator of H2, which is integers. So that is it. You see, alpha cup beta generates H2, alpha cup alpha is 0, and beta cup beta is 0. Now you can extend this to 2-hole torus. So how do you extend this to 2-hole torus? I'm going to copy this entire thing down to right here. You have 0, you have 1, you have 2, and you have 3. And then you have precisely like this, you have alpha and beta. So we will have, so this torus here we will have A1, A1. I'm just exactly copying this. B1, B1. This you call as alpha 1, and then you have corresponding this you call as beta 1. So this torus, you cut a hole right here. So there is a hole right here. So when you glue it, and what you get is something like this. And this hole comes right here. Similarly, you can have this torus. On this torus, I will say you say 0 prime, 1 prime, call it 3 prime, and you call this 2 prime. And again you have a hole right here. And here you say these edges are A1, say this is A2, this is A2, this is B2, and this is B2. And again you have these alphas and betas. So this you call as alpha 2, and this you call as beta 2. And you can glue this with the, you can again glue this part and you will get a torus like this. And this is the yellow part. Glue these two together. This you glue with this, and you get a 2-hole torus. So the 2-hole torus will look like this. So this yellow part is coming right here. So if you open it up, all these vertices you write down like this, and you open it up, this is what you're going to get. So this is exactly the yellow line, and I'm going to write this part here, 0, 1, 2, 3, and here I'm going to write 0 prime. Okay, so let us just focus on this part here. So again you will have this alpha 1. This alpha 1 is connecting 0, 1, which is going in this direction. 0, 1 is going in this direction, 1, 2 is here, and then these two are in opposite directions. So the 0, 1 is connected to 2, 3. So this is the connection. This is alpha 1. So this is alpha 1, and then you have this is beta 1. And then you could do the same analysis here, and you can find that alpha 1 cup with alpha 1 is 0, beta 1 cup with beta 1 is 0. Yeah. Similarly, you will have alpha 2 cup with alpha 2 is 0, beta 2 cup with beta 2 is 0. So you have alpha 2 cup with alpha 2 is 0, and similarly beta 2 cup with beta 2 is 0. So that is clear. Now alpha 1 cup with alpha 2 is also 0. Why is that? So alpha 2 is in a completely different space. So for example, so say you have alpha 1 cup alpha 2, and you make it act on some triangle here. Say you make it act on 0, 1, 2. Now alpha 2 doesn't even lie here. So alpha 1 can take whatever value in 0, 1, but alpha 2 will always be 0 on this torus. On this part, alpha 2 will always be 0, but alpha 1 lies precisely in this part. So whenever you cup alpha 1 with alpha 2, you will get 0. Similarly, alpha 2 lies in this part. If you try to cup alpha 1 with alpha 2, it will be 0, because if you consider triangulation in this torus and apply alpha 1 to any of the edges, that will be 0, because alpha 1 is only acting on edges in this torus. So you have alpha 1 cup alpha 2 is 0, beta 1 cup beta 2 is 0, and you have alpha 1 cup beta 1 just like here as integers. So this you can say is 1, and alpha 2 cup beta 2 is also 1, that is generated from here. And these are the two parts which will generate H2. So H2 is generated by alpha 1 cup beta 1 and alpha 2 cup beta 2.